Now we want to find the area and length. We're not going to focus much on length, it's more of an area of anything. Remember that if we call this S equal R times theta, and if you wanted to find that area of the shaded region, that's 1/2 R squared theta. The deal was theta must be in radians, if you recall. Now we would like to find the area of a polar graph. Let's say we're given R equal f of theta. And if I would like to run this and find the area between those two angles, let's say I want to run and find the area from angle theta. I'm going to shrink this a bit since we don't need that for this section. Just wanted to remind you of how that works. If we want to find the area from theta to beta, what we do, we break this into slices just like we did with the rectangular. And if I take one of those, let's say I take this and I enlarge that, I'm really looking at something that looks like this, in which f of theta is actually an arc. And now if I take this slice and I find its area, well, that is R right there. And I would say the area for that, so the area sub I is going to equal 1/2 R sub I times theta sub I. And you know the drill. If I sum them up from alpha to beta, I'll get the whole thing. And area would equal the integral from alpha to beta. And that's how theta is going to vary. And 1/2 R squared, or f of theta, however you want to see it. And if I wanted to find the area of a sector in which I have R equal f of theta, and R equals some g of theta, and if I wanted to find the following area, just like we did with rectangular coordinates, you know how when we drew our rectangles we picked top minus bottom? The difference here is when I draw my arrows, instead of looking at a rectangular piece and say, well, look at the top minus the bottom, here I take the tip minus the base. Basically, I'll find the whole area. I'll find this area and subtract the two. So area here would be the integral, again, let's say from alpha to beta. Oh, I messed up. From alpha to beta of 1/2, and the same caution or warning that we did, you actually take f of theta squared and you subtract off g of theta squared. You don't take f of theta minus g of theta quantity squared, kind of like when you did back in the days when you found the shell method and washer. So that's pretty much how it works. Now let's look at some examples. And here I'm going to set up all of these integrals, and most of them, since you're squaring a sine or a cosine, you're going to have to use section 7.2, integrals of trig functions. Remember that power reduction, sine squared is 1 minus the cosine of 2 theta divided by 2, and cosine squared is 1 plus the cosine of 2 theta divided by 2. If I want to find the following, and again, only numbers 6 and 8, they give you the graph. The rest you have to graph yourself. area would be the integral. And if I glance at this and notice, this starts at pi over 2 and it terminates at pi. And if I run my arrows, tip of the arrow minus the base, it seems the tip is always this function and the base is 0. So I'm going to say it is 1/2 and r is 2 plus the cosine of theta squared d theta. And that's pretty much it. You FOIL, you know, and go from there. So you're going to get a cosine or a sine squared in every problem, right? And we call that sine squared of theta is 1 minus the cosine of 2 theta divided by 2. And cosine squared of theta is 1 plus the cosine of 2 theta divided by 2. When I get to the next problem, number 8, I am looking at the area, and area is going to be the integral. And here I notice that this starts at 0, and it looks like it is running all the way to 2 pi. So if I run my arrows, I'll notice you're always running from the origin. That's always how it works. And it looks like I'm going to trace all the way till the end the square root of natural log of theta squared d theta. And there it is with all the excitement. I forgot to give you a page. This would be on page 712 in our book. So keep in mind, on the exam, most likely the majority of what I want is the setup, since the integration is the same for almost all of those. And just like we graphed those, we really don't want to pick points. We know that r equal 1 because it's a vertical shift, and the amplitude we go 1 above and 1 below. So if I start at 1, go up 1 unit and down 1 unit, a sine wave starts at the origin. Since this is reflected, instead of running up, it's going to run down, back up, and back down. And if you recall, we're going to get a quick graph. At 0, I am at 1. There's 0, there's 1. Decreases, and 2 pi, pi over 2, and 3 pi over 2. By the time I hit pi over 2, there's pi over 2. R will equal a 0. So this is going to shrink down to 0. And then after that, it's going to increase. By the time I hit pi, I am at 1 again. There's pi and there's 1. It keeps on increasing. By the time I hit 3 pi over 2, I know that r equal 2. There's 3 pi over 2 and there's 2. The grid will be provided on the exam. And we know it's going to go back. We knew this was a heart shape wrapped around the negative y-axis. And if I start tracing, I notice that from 0 to pi over 2, I'll get that much. To pi, I'll get that much. To 3 pi over 2, it seems this area would be the integral from 0 to 2 pi of 1/2, and r is 1 minus the sine of theta squared divided by squared d theta. I do want to give you a heads up. Not all of the graphs, actually very few graphs you run from 0 to 2 pi to trace the whole graph. Sometimes before that you trace it. So you can't say 0 to 2 pi on almost any of those. There are only a couple of exceptions. Majority of those you must get the graph right for this to work. And here we have a vertical shift of, again, we know this is a graph wrapped around the negative x-axis. I'll talk about that in a minute. So we're going to go up 2 units. 1, 2. Just shift that up just a bit more. Here we go. R equal 2. And we label that. And we're going to run 1 unit here we go. And we're going to run 1 unit above to r equal 3 and 1 unit below to r equal 1. Oh, look at that. I caught it again. Okay, and a cosine graph starts from the amplitude, but this is reflected, so it starts once up, back down. That's 1 full revolution. And here there's no shifting. and this is 2 pi, this is pi, pi over 2, and 3 pi over 2. So we know this is a graph that's wrapped around the negative x-axis, and we know there's no loop because r is always positive. Again, that's from 10.3. Now, at 0, I am at 1. There is 0, there is 1. Increases. By the time I hit pi over 2, I am at 2. There is pi over 2, and there is 1, 2. And keeps on increasing. By the time I hit pi, r equal 3, there's pi, and there's 1, 2, 3. Keeps on increasing, and there it is. I could copy the bottom half, I could get it off the graph, start decreasing. By the time I hit 3 pi over 2, I am at 2, and keeps on decreasing. By the time I hit 2 pi, it goes back to the traditional. And again, if I draw my arrows, I notice that I'm running from the origin to the actual function all throughout, no exceptions. And I could trace the whole graph, and this does run from 0 to 2 pi. Again, that's an exception. I would say area equal the integral from 0 to 2 pi of 1/2 r squared d theta, and this becomes old really quickly. So the work is really the graph and the trig. On this graph, we're going to ignore the square for now. We're going to say, well, r equal 4, 1, 2, 3, 4, 1, 2, 3, 4. We're ignoring the square altogether. R equal 4 and r equal a negative 4. A graph of a cosine starts on the amplitude, runs down to the amplitude, back to the starting point, and there it is. Now this is 2 pi divided by 2, which is pi. This is pi over 2. This is half of it, pi over 4, 2 pi over 4, 3 pi over 4. And here I'm going to make use of symmetry, so I don't need those 30 and 90. I just need the pi over 4s. I already have them over there. And the way this works, at 0 I am at 4. At 0 I am at 2. I could label those anywhere I want. 4. Decreases. By the time I hit pi over 4, r equals 0. There's pi over 4, there's 0. Pretty much I'm done with this graph because of symmetry, and I know it's going to take from the previous section 11.3. I know this is, since this is even, this is a 4-leaved graph, and those leaves are going to be 2 pi over 4 apart. So wherever one maxes 1 pi over 4, 2 pi over 4, it's going to happen again. 1, 2, so 0, 1 pi over 4, 2 pi over 4, 3, 4, 5, and another one right there. That's the graph of r equal 4, the cosine of theta. But when I square root both sides, when I square root this, I'll get 2 plus or minus is going to be symmetric. But this tells me, since this is underneath the radical, this quantity gonna be negative, and this graph gives it all. I noticed that r is negative between pi over 2 and 3 pi over 2. Between pi over 4, I'm sorry, and 3 pi over 4. Since r is negative, I can't have that. And since the graph is symmetric, that's not gonna exist as well. And since that's a 2, all what I have to do is alter this. I can scale it any way I want. So the area that I really want to find would be this area and this area. Well, very simple. I could do this so many different ways. I'm going to integrate from 0. And do you notice I'm always running to the function? I'm going to run to pi over 4 of 1/2 r squared d theta. R squared is already given to before the cosine of 2 theta. Cosine of 2 theta, and since there is 1, 2, 3, 4 of those, I multiply that by 4 and use symmetry, and that will do the trick. You could do this, of course, from negative pi over 4 to pi over 4. If you're going to put the limits on the integral, make sure they are in ascending order from lowest to highest. It looks like this is it for this video. On the next video, I'll do the remaining evens.